Monad equation in the logistic approach, continuous and discrete models for substrate replacement. This is a presentation for 14th International Conference of Mathematical Modeling in Physical Science, presented by Estela Delgado Ceballos and Francisco Delgado. In this result, we follow the following outline. First, the monad equation and applications. Then we present the monad equation particularly together with the logistic model domain. Then the reparametrization for this equation using a minimal number of parameters. Then we present a couple of substrate replacement models, one continuous and another discrete. Then we talk about the monad equation as a dynamical system. Then we observe the periodical behavior that those substrate replacement models have and their relation with the Poincaré-Bendixson theorem. Then, as a result, we talk about the characterization based on periodical behavior and finally our conclusions. Well, the monad equation was constructed as a competency resource models for specific populations in biotechnology, but this model was spread to other disciplines, by example, economy, technology, sociology, ecology. In this table, we shown the main variable representing the main population being described, normally not necessarily a biological species in this case for marketplace or memory amount in economy of technology, by instance. Then the last column show the secondary variables depicting the substrate amount of some elements or some resource feeding the first main population here. In the case of biology, we normally use this model to depict the bacterial growth here, and the substrate is the feed for this species of bacteria, for example. But the use is not only restricted to bacteria, of course. Then here is the monad equation. This is basically a relation between the amount of some substrate here in terms of the variable k, which state the minimum value of for the mu or rate of growth of population in another model, because this equation, monad equation, needs another differential equation to depict the relation between two species. Then monad equation is a chain linking two models between the the main populations under study, together with another serving as a substrate or food for the first one. In this work, we particularly use the logistic model represented here, and the derivative of n, the number of elements in the main population here, depicting or depicted in terms of the growth rate here, included in the monad equation, together with the maximum number of elements in the population as a restriction imposed by the environment of the main population here. Normally, n is modeled in terms also of the amount of the substrate, because it is possible the first element restricting the maximum number of elements. But here n could depend on another variables are the pH or, for example, the temperature in the case of biology, or another additional external parameters regarding the model. In this case, we don't use external parameters, only we relate the maximum number of in this logistical model with the number of the or amount of the substrate also here. Then we combine this couple of equations here, but we need a differential equation regarding the number of the amount of the substrate here in terms of this derivative of time, relating the amount as decreasing depending on the number of the elements in the first population here. Quay is a number relating the number of the main population elements here with respect to with the amount of the substrate here. No? In addition, we add a function R here, we depicts the possibility to fit the amount of the substrate here in terms of time. This in this case R is the amount introduced continuously or discretely through the time to compensate the waste made by the main population here. These equations normally depicts very well the growth of the biological species. For example, having a latency stage, then the growth, normally an exponential growth, as logistical model does, and then a stage stationary here, and finally death here. Then monodic equation relate both species, the main species under study here, with the substrate feeding the first one here. Then in the following slides, we present the main outcomes here, and we are moving with the models of R in terms of periodical functions. Here we've shown the relation between the amount of the substrate here with mu, the growth rate for the main population here, and we observe how the medium value of the maximum growth rate is reached here in terms of the value of the S here in the green dot. We have the K S, the value Ks, which states the fast or the velocity for the growth of the population here. No? In this case, this Ks value, if it occurs before in time, we have a faster growth for the main population. We in the lower plot we observe a couple of examples regarding the number of elements in one population here. For example, for the dotted lines here, we observe the behavior for the substrate, and the continuous lines depict the main population here. For black plots, we observe the case when we don't replace the substrate, then the population, the continuous line, growth, have a stability period, and then a decreasing the death of the population. If any case we introduce the replacement of the substrate here, for example, through the plot, in this case the plot here. In this case, we have a little replacement here. This is the green or blue line, dotted line here. This is there are different to zero replacement of substrate. Then we have a rise of the number of the main population. Well, this equation can be solved normally numerical because it's difficult to solve analytical here, but there are some exceptions, of course. And here we note that this group of equations can be written in terms of the different values here. If we note through the logistical model presented before in the previous slide, we can introduce together with n these constants here, and additionally here together with s. Here we replace the maximum number of elements in the population here, and we have then change in this equation in terms of the variables. We can change the number of elements in the main populations as new here, and the amount of the substrate here in terms of sigma. This is possible by changing together the time through this renormalized time here, introducing the kappa parameter here instead of y, and together replace the replacement function r in terms of rho, this normalized function for the replacement here. Then our equation remains or becomes here this couple of equations where we are substitute the relation for maximal number of elements in the population. With this behavior, we can show or introduce a couple of models for the replacement of amount of the substrate here. This is continuous in terms of a sim function, and this is another discrete function introducing only additional substrate amount in some parts of the time. Both functions have a period p here. The behavior in terms of the renormalized time is shown here. For the line yellow is the substrate here in two models, and the blue line represents the amount of the number of elements in the population in terms of these representative variables nu and sigma. This another view is the representation for this dynamical system in the phase space. Here is nu and here is sigma for the continuous model or for the discrete model. No? The beginning of the behavior at time t equal to 0 is here and here. Then the evolution go through this curve, these periodical curves here, or almost periodical. And this is the main topic here introduced in the next slide, because this model is independent of time with exception of the function rho here introduced as a periodical function. Then this dynamical system have a behavior which for larger times have limit cycles shown here, for example, for the continuous model and the discrete model here. And we can observe that independently of the initial condition shown here, the final curve is the same. Then this model depends only from the kappa parameter and the replacement function be used. And in these replacement models, we have only one parameter, rho sub 0, which is the strength of the amount of the substrate being introduced in function of the time. Then we have an interesting behavior because the Poincaré-Bendixson theorem in mathematics lets to show that these limit curves are independent of another parameters only in terms of kappa and rho sub 0, because the model are different. But the another qualities or characteristics are lost. For example, the period, it's in the phase space is independent of the period. Then it is very interesting because we have or can introduce the study of some parameters or characteristics depicting our system or both systems, the population together with the substrate, because the periodical behavior, for example, this amount represents the number of elements in average in by cycle in the population with respect by each number of the amount of the substrate here. Then the epsilon is amount characterizing the population, and particularly we shown here in color the behavior in terms of kappa and rho sub zero. In the corners we have the behavior shown here by the limit cycles here, and this is for the continuous and this is for the discrete behavior. This is very interesting because we have a similar behavior despite the behavior for the limit cycles in the corners shown as only as an example. It's very different, but the behavior for epsilon it's very similar in general for this representation. Now, this is of course an example for biotechnology applications in terms of bacterial growth, for example, but another similar aspects can be analyzed or studied in terms and other parameters, inclusively for biotechnology, because it is characterizing the behavior of the periodical cycle obtained for larger times. Then our study has shown that monod equation is applicable in multiple disciplines to describe the competence between two or more resources, as those shown here in terms of the biotechnology discussions. The monod equation was analyzed together with the logistical growth model, which is very common here in biotechnology, in terms of improve this basic model of growth. Two substrate replacement models were introduced, one continuous and another discrete, in terms of use as model to feed the dynamical system studied here. Real model was transformed, in this case, in another dimensionless model based only in basically two parameters, kappa in the first part, and another introduced through the feeding replacement model for the substrate in terms of rho sub zero, which is the strength of this replacement. In addition, of course, particularly the type of model, no continuous or discrete, as was shown in our previous slides. The dynamical model exhibits, in this case, limit cycles. Note that this is only possible in 2 dimensions because the Poincaré-Bendixson theorem and these limit paths are obtained or are different or are characterized by the parameter kappa introduced in our discussion. This behavior, the limit cycle, has allowed us studying associated quantities to the problem in particular, because the periodical behavior becoming in terms of this periodical path let's state certain features for our behavior in the dynamical system, and this is very interesting in this case study based on the properties of the dynamical system introduced here using mainly monod model together with the logistical model and particular or introduced parameterization in terms of only few parameters. Then this is all talk. Thank you very much for your attention, and we put here our email in case of communication for the continuous discussion of this topic. Thank you so much.